welcome to all of you. I am Coulomb Ganguly, Assistant Teacher of Shampur High School, District Hooghly, State West Bengal. Today, I am going to discuss Coulomb's law. French scientist Charles Coulomb experimentally measured the electric forces between the two small charged metallic spheres by using a torsion balance. He performed so many experiments to know how does the electric forces depends on the magnitude of the charges. How does the electric forces depends on the separation between the charges. To find out the relation between electric forces and magnitude of the charges, he varied magnitude of the charges, kept distance between them constant, and to find out the relation between electric forces and distance between the charges, he varied distance between the charges, kept magnitude of the charges constant. A series of careful measurements led Charles Coulomb to the law of electric forces between the 2-point charges. This law is called Coulomb's law. Coulomb's law stated as the force of attraction or repulsion between the two stationary point charges is directly proportional to the product of the magnitudes of the two charges and inversely proportional to the square of the distance between them. This force acts along the line joining the two charges. Now, the question is, what is point charge? When the linear size of the charged objects are very small compared to the distance between them, then the size may be ignored and the charged objects are treated as point charges. For example, suppose two similar sized charged objects, spherical shaped, of diameter 1 millimeter, separated by a distance of 100 meters. Now, linear size of the charged objects is very small compared to the distance between them. So, both the charged objects are treated as point charge. Now, we know two like charges repels each other, whereas two unlike charges attracts each other. Suppose 2-point charges Q1 and Q2 separated by a distance are and situated at points A and B respectively. If Q1 and Q2 have same sign, suppose Q1 is positive and Q2 is positive, then Q1 repels Q2 along AB and Q2 repels Q1 along BA. If Q1 and Q2 have opposite sign, suppose Q1 is positive and Q2 is negative, then Q1 attracts Q2 along BA and Q2 attracts Q1 along AB. In both the cases, electrostatic forces acts along the line joining the two charges. So, due to this reason, electrostatic force is called a central force. Do you know what is central force? A force which acts along the line joining the centers of the two interacting objects is called central force. So, it is clear to us why we called electrostatic force is a central force. Okay. Suppose 2 point charges Q1 and Q2 separated by a distance r, and F is the electrostatic force between them. Now, according to Coulomb's law, we can write F varies as Q1, Q2 when R is constant, and F varies as 1 by R square when Q1, Q2 are constant. Now, combining these two equations, we can write F varies as Q1, Q2 by R square when Q1, Q2 and R are variables. So, we can write F equals to a constant K Q1, Q2 by R square, where K is a proportionality constant. K is referred to as electrostatic constant or electrostatic force constant. Now, the value of electrostatic constant depends on the nature of the medium between the 2 point charges and the system of units chosen to measure force, distance and charge. Now, if we consider the 2-point charges situated in vacuum, then the electrostatic constant K in SI units written as K equals to 1 by 4 pi epsilon 0. The value of electrostatic constant in SI units for vacuum is experimentally found to be 8.98755 into 10 to the power 9 Newton meter square per Coulomb square. And in many calculations we use its approximate value. The approximation value of K is 9 into 10 to the power 9 Newton meter square per Coulomb square, where epsilon 0 is a constant referred to as absolute electrical permittivity of free space, simply called permittivity of free space. Now, what is the value of epsilon 0? From this equation, we can write epsilon 0 equals to 1 by 4 pi into 9 into 10 to the power 9 Newton meter square per Coulomb square, which is equals to 8.854 into 10 to the power minus 12 Coulomb square per Newton per meter square. So, the formula of Coulomb's law in SI units for vacuum is F equals to 1 by 4 pi epsilon 0 Q1 Q2 by R square. equation 5, we can write epsilon 0 equals to 1 by 4 pi Q1 Q2 by FR square. Using this equation, we can derive the dimensional formula of epsilon 0. So, dimensional formula of epsilon 0 equals to dimensional formula of Q1 into dimensional formula of Q2 by dimensional formula of F into dimensional formula of R square. Now, dimensional formula of epsilon 0 equals to dimensional formula of charge is IT. So IT into IT by dimensional formula of force is ML T to the power minus 2 into dimensional formula of R square is L square, or dimensional formula of epsilon 0 equals to n to the power minus 1 L to the power minus 3 T to the power 4 I square. Now, we can also derive the units of epsilon 0 using these equations. We know that SI unit of charge is Coulomb, SI unit of force is Newton, and SI unit of distance is meter. So, what comes out from this equation? That the unit of epsilon 0 is Coulomb into Coulomb, Coulomb square by Newton into meter square. Coulomb square per Newton per meter square. Now, this is the unit of epsilon 0. Now, we can write this unit as Coulomb into Coulomb, Newton into meter equals to Coulomb into Coulomb, Newton into meter equals to Joule. Joule into meter. We know that Joule per Coulomb equals to volt. So, this can be written as Coulomb by volt into meter. And again, Coulomb by volt equals to farad. So, this is equals to farad per meter. So, farad per meter. So farad per meter is another unit of epsilon 0. This is very important for competitive exam. Now, in CGS system, for vacuum, the electrostatic constant K equals to 1. So, the equation of electrostatic force F equals to Q1 Q2 by R square. Now, units of charge. The SI unit of charge is Coulomb. Symbol of Coulomb is capital C. Now, Coulomb's law in SI units for vacuum is expressed as F equals to 1 by 4 pi epsilon 0 Q1 Q2 by R square. Let Q1 equals to Q2 equals to Q. R equals to 1 meter. F equals to 9 into 10 to the power 9 Newton. Now, from equation 1, we get 9 into 10 to the power 9 equals to, we know the value of 1 by 4 pi epsilon 0 equals to 9 into 10 to the power 9 Newton meter square per Coulomb square. 9 into 10 to the power 9 Q square by 1 square, or Q square equals to 1, or Q equals to plus minus 1 Coulomb. So, 1 Coulomb is that charge which repels an equal and similar charge when placed at a distance of 1 meter from it in vacuum with a force of 9 into 10 to the power 9 Newton. Some smaller units of charge are 1 millicoulomb equals to 10 to the power minus 3 coulomb. 1 microcoulomb equals to 10 to the power minus 6 coulomb. 1 nanocoulomb equals to 10 to the power minus 9 coulomb. In CGS system, unit of charge is ESU of charge or stat coulomb or Franklin. So, 1 ESU of charge equals to 1 stat Coulomb equals to 1 Franklin. Coulomb's law. In CGS system for vacuum is expressed as F equals to Q1 Q2 by R square. Let Q1 equals to Q2 equals to Q, R equals to 1 semi, F equals to 1 die. From equation 2 we get 1 equals to Q square by 1 or Q square equals to 1 or Q equals to plus minus 1 ESU of charge. So 1 ESU of charge is that charge which repels an equal and similar charge when placed at a distance of 1 centimeter from it in vacuum with a force of 1 dyne. Relation between Coulomb and ESU of charge is 1 Coulomb equals to 3 into 10 to the power 9 ESU of charge. Another unit of charge is EMU of charge, which is also called Coulomb. 1 EMU of charge equals to 1 Coulomb equals to 10 Coulomb. Okay. Now, numerical problems. Problem number 1. A pith ball of mass 10 to the power minus 2 kg carries a charge 9.8 microcoulomb. Suppose this is a pith ball. Charge of this pith ball Q1 equals to 9.8 microcoulomb equals to 9.8 into 10 to the power minus 6 coulomb. Mass of this pith ball M1 equals to 10 to the power minus 2 kg. Next, another pith ball of equal mass is placed 0.06 meter above the first ball. This is the second pith ball. Mass of the second pith ball M2 same as first ball. M2 equals to 10 to the power minus 2 kg. Another pith ball of equal mass is placed 0.06 meter above the first ball. So, the separation between the two pith ball R equals to 0.06 meter. Next, what charge is given to the second ball? What charge is given to the second ball so that the ball will remain in equilibrium? This ball will remain in equilibrium. Suppose charge of the second ball will be Q2. Now, the question is, what charge is given to the second ball so that the ball or the second ball will remain in equilibrium? Equilibrium means net force on second ball will be 0. Now, weight of the second ball W2 equals to M2G acts along vertically downward direction. So, electrostatic force F on the second ball will be act along vertically upward direction, and F would be equals to W2. Then net force on the second pith ball would be 0, and the second pith ball will remain in equilibrium. Okay. Now, this electrostatic force must be repulsive. So, the sign of Q2 will be same as Q1, that is positive. We know from Coulomb's law that F equals to 1 by 4 pi epsilon 0 Q1 Q2 by R square. So, from equation 1 we can write 1 by 4 pi epsilon 0 Q1 Q2 by R square equals to M2G, where small g the gravitational acceleration, or value of 1 by 4 pi epsilon 0 is 9 into 10 to the power 9 Newton meter square per Coulomb square. Q1 9.8 microcoulomb, or 9.8 into 10 to the power minus 6 Coulomb. Q2, we have to find out the value of Q2 by R square. R equals to 0.06 meter. 0.06 square equals to m2g. m2 equals to 10 to the power minus 2 kg into g. We know value of gravitational acceleration in SI units equals to 9.8 meter per second square. Or Q2 equals to 0.06 square into 10 to the power minus 2 into 9.8 by 9 into 10 to the power 9 into 9.8 into 10 to the power minus 6 equals to 4 into 10 to the power minus 9 Coulomb, or Q2 equals to 4 nano Coulomb. Now problem number 2. Two small spheres A and B, each having mass m kg and charge q Coulomb, are suspended from a point O by insulating threads, each L meter long but of negligible mass. If theta is the angle each thread makes with the vertical when equilibrium has been attained, so that q square equals to 4 pi epsilon 0 into 4 mg L square into sine square theta into tan theta. Now, what is the situation in equilibrium? O is the point of suspension. These are the two threads A and B are two small spheres. This is the vertical line and theta is the angle each thread makes with the vertical when equilibrium has been attained. So, this angle is theta and also this angle is theta. Now, why these two threads makes an angle theta with the vertical? Suppose both the spheres have no charge, then what will be the situation? The situation will be this, and they are now charged. Due to their charges, both the spheres repels each other and moves away from each other. And when equilibrium has been attained, both the threads makes an angle theta with the vertical. Now, equilibrium means net force 0. So, net force on A will be 0. Net force on B will be also 0. Now we consider equilibrium of sphere A. Now, what forces acting on sphere A in equilibrium? weight mg of the sphere acting vertically downward direction. Electrostatic repulsive force F acting along BA direction. Tension T of the thread directed towards point of suspension O. Now let's draw OD perpendicular AB. Now it is clear from figure that D will be the midpoint of AB. Now from triangle OAD, we can write AD by OA. AD by OA equals to sin theta, or AD equals to OA sin theta. OA equals to L, or AD equals to L sin theta. So AB equals to 2AD. AB equals to 2AD because D is the midpoint of AB, or AB equals to 2L sin theta. Now electrostatic force F written as F equals to 1 by 4 pi epsilon 0 Q square by AB square, or F equals to 1 by 4 pi epsilon 0 Q square by AB equals to 2L sin theta. So AB square equals to 4L square sin square theta. 4L square sin square theta. Now we resolve tension T into two rectangular components. From figure, it is clear that this angle will be theta. So vertical component of tension T is T cos theta, and horizontal component of T is T sin theta. Now for the condition of equilibrium, we can write T sin theta equals to F and T cos theta equals to mg. Dividing equation 2 by 3, we get T sin theta by T cos theta equals to F by mg. or tan theta equals to F by mg, or F equals to mg tan theta, or one by 4 pi epsilon 0 q square by 4l square sine square theta equals to mg tan theta, or q square equals to 4 pi epsilon 0 4 mg l square into sine square theta into tan theta. Proved. Okay. Now, comparison between electrostatic and gravitational forces. There are some similarities and some differences between the electrostatic force and gravitational force. Electrostatic force between the 2 point charges Q1 and Q2 separated by a distance r is expressed as Fe equals to K Q1 Q2 by r square, where K is electrostatic constant, and gravitational force between the 2 point masses m1 and m2 separated by a distance r is expressed as Fg equals to capital G m1 m2 by r square, where capital G is universal gravitational constant. Now, some similarities between these two forces are: electrostatic force Fe varies as 1 by r square. So, electrostatic force obeys inverse square law, and gravitational force Fg varies as 1 by r square. So, gravitational force is also obeys inverse square law. Electrostatic force is a central force, and gravitational force is also a central force. Electrostatic force is a conservative force, and gravitational force is also a conservative force. Now, some differences between the electrostatic force and gravitational force are: electrostatic force may be attractive or repulsive. We know two like charges repels each other and two unlike charges attracts each other, whereas gravitational force is always attractive in nature. Electrostatic force between the 2-point charges is depend on the nature of the medium between the 2-point charges. So, electrostatic force is medium dependent, but gravitational force is medium independent. Electrostatic force is much stronger than gravitational force. Let's discuss an example. Suppose two electrons separated by a distance r and situated in vacuum. We know electron is a negatively charged particle. If the magnitude of charge of an electron is small e, then electrostatic repulsive force between the two electrons written as Fe equals to 1 by 4 pi epsilon 0 square by r square. Now, if small m is the mass of an electron, then gravitational attractive force between the two electrons is written as Fg equals to capital G m square by r square. Dividing equation 3 by 4, we get Fe by Fg equals to 1 by 4 pi epsilon 0 square by capital G m square, or Fe by Fg equals to, we know 1 by 4 pi epsilon 0 equals to 9 into 10 to the power 9 Newton meter square per Coulomb square. Here we consider magnitude of charge of an electron E equals to 1.6 into 10 to the power minus 19 Coulomb. Capital G or gravitational constant in SI units equals to 6.67 into 10 to the power minus 11 Newton meter square per kg square, and mass of an electron m equals to 9.11 into 10 to the power minus 31 kg. So, Fe by Fg equals to 9 into 10 to the power 9 Newton meter square per Coulomb square into 1.6 into 10 to the power minus 19 Coulomb square by 6.67 into 10 to the power minus 11 Newton meter square per kg square into 9.11 into 10 to the power minus 31 kg square. Calculating this, we get Fe by Fg equals to 4.16217 into 10 to the power 42. So, the ratio of the electrostatic force to the gravitational force between the two electrons is 4.16217 into 10 to the power 42. So, it is clear that electrostatic force is much stronger than gravitational force. Now problem number 3. A particle of mass m and carrying charge minus q1 is moving around a charge plus q2 along a circular orbit of radius r. Find the time period of revolution of the charge minus q1. Here, the charge plus q2 is fixed and another charge minus q1 is moving around q2 along a circular orbit of radius r. Suppose speed of the charge minus q1 is v. Here, the necessary centripetal force is provided by electrostatic force of attraction between the two charges. The magnitude of electrostatic force of attraction F equals to 1 by 4 pi epsilon 0 q1 q2 by r square. So we can write mv square by r equals to F, or mv square by r equals to 1 by 4 pi epsilon 0 q1 q2 by r square, or v square equals to 1 by 4 pi epsilon 0 q1 q2 by mr, or v equals to root over 1 by 4 pi epsilon 0 q1 q2 by mr. Suppose capital T is the time period of revolution. Here time period means time taken by this charged particle to make one complete revolution. So, capital T equals to 2 pi r by v, or capital T equals to 2 pi r into root over 4 pi epsilon 0 mr by q1 q2. Okay. Now, Coulomb's law in vector form. This is very important for class 12 exam. Suppose 2-point charges q1 and q2 both have positive sign separated by a distance r, situated at points A and B respectively and located in vacuum. Now, the electrostatic force between the 2-point charges in SI units written as F equals to 1 by 4 by epsilon 0 Q1 Q2 by R square. This is the scalar form of Coulomb's law. Now, we have to express this electrostatic force in vector form. That will be the vector form of Coulomb's law. Here we consider both the charges have positive sign. We know two like charges repels each other. So Q1 repels Q2 along AB and Q2 repels Q1 along BA. Now, we denote force on Q2 due to Q1 as F21 vector and force on Q1 due to Q2 as F12 vector. Now, if we want to express this force in vector form, we have to find out the unit vector along AB vector. Suppose position vector of A is R1 vector and position vector of B is R2 vector. So we can write R1 vector equals to wave vector and R2 vector equals to OB vector. Now, according to triangle law of vector addition, from triangle OAB, we can write OA vector plus AB vector equals to OB vector, or AB vector equals to OB vector minus OA vector. If we denote AB vector as R21 vector, then we can write R21 vector equals to R2 vector minus R1 vector. So we can write unit vector along R21 vector as R21 cap equals to R21 vector by mod of R21 vector. Similarly, we can write BA vector as R1 vector minus R2 vector, and if we denote BA vector as R12 vector, then we can write R12 vector equals to R1 vector minus R2 vector, and unit vector along R12 vector written as R12 cap equals to R12 vector by mod of R12 vector. It is clear that AB vector and BA vector are opposite vector. So, modulus of AB vector equals to modulus of BA vector, or mod of R21 vector equals to mod of R12 vector, and also we can write R21 cap equals to minus R12 cap. Now, we can write F21 vector as F21 vector equals to 1 by 4 pi epsilon 0 Q1 Q2 by square of R21 vector mod into R21 cap. Now, if the charges have opposite sign, then what will be the vector form of Coulomb's law? Suppose Q1 is positive and Q2 is negative. We know two unlike charges attracts each other. So Q1 attracts Q2 along BA, and Q2 attracts Q1 along AB. So, the direction of F21 vector is along BA. We can explain this using equation 2. When the charges have opposite sign, then the sign of product Q1 Q2 will be negative, and a negative sign before R21 cap equals to R12 cap. So the direction of this force F21 vector along R12 cap. So it is clear that whatever the sign of the charges, this is the vector form of Coulomb's law. Now we can write F12 vector as F12 vector equals to 1 by 4 pi epsilon 0 Q1 Q2 by square of mod of vector R12 into R12 cap equals to 1 by 4 pi epsilon 0 Q1 Q2 by, we know, mod of R21 vector equals to mod of R12 vector. So we can write this as R21 vector mod square and R12 cap. From this equation we can write R12 cap as minus R21 cap minus R21 cap. So F12 vector equals to minus F21 vector. So from this equation we can say Coulomb's law obeys Newton's third law of motion. Okay. Now problem number 4. 2-point charges Q1 equals to 2 microcoulomb and Q2 equals to 6 microcoulomb are located at A and B. Find F21 vector using Coulomb's law. Suppose position vector of point A is R1 vector and position vector of point B is R2 vector. So R1 vector equals to 3i cap plus 5j cap plus k cap and R2 vector equals to 5i cap plus 6j cap plus 3 k cap. Now R21 vector equals to R2 vector minus R1 vector, or R21 vector equals to R2 vector 5i cap plus 6j cap plus 3k cap minus r1 vector minus 3I cap minus 5j cap minus k cap, or r21 vector equals to 2I cap plus j cap plus 2k cap. So modulus of vector r21 is mod of r21 vector equals to root over 2 square plus 1 square plus 2 square equals to root over 4 plus 1 plus 4 equals to root over 9 equals to 3 meter. So unit vector along r21 vector is r21 cap equals to r21 vector by mod of r21 vector equals to 2I cap plus j cap plus 2k cap by 3. Now, using Coulomb's law, we can write F21 vector as F21 vector equals to 1 by 4 by epsilon 0 Q1 Q2 by R21 vector mod square into R21 cap, or F21 vector equals to, we know, value of 1 by 4 by epsilon 0 equals to 9 into 10 to the power 9 Newton meter square per Coulomb square. Q1 equals to 2 microcoulomb. 2 into 10 to the power minus 6 coulomb into Q2. Q2 equals to 6 microcoulomb. 6 into 10 to the power minus 6 coulomb by R21 vector mod square, which is equals to 9 meter square into R21 cap. 2I cap plus j cap plus 2k cap by 3. Calculating this, we get F21 vector equals to 4 into 10 to the power minus 3 2I cap plus j cap plus 2 cap Newton. Okay. Now, principle of superposition. We know Coulomb's law gives electrostatic force between the 2 point charges only. But if there is a system of point charges, then how do we find the total force on a given point charge due to the other point charges? Principle of superposition gives a method to find this force. Now, according to principle of superposition, when a number of point charges are interacting, then the total force on a given point charge is the vector sum of all the individual forces on that point charge due to the other point charges taken one at a time. the force between any 2-point charges is unaffected due to the presence of other charges. Suppose a system of n-point charges Q1, Q2, Q3 and so on till Qn located in vacuum, and all the point charges are stationary. Now, suppose the point charge Q1 situated at point A1 and position vector of point A1 is R1 vector, and point charge Q2 situated at point A2 and the position vector of point A2 is R2 vector. Similarly, point charge Qn situated at point An and the position vector of point An is Rn vector. Now, what will be the total force on point charge Q1 due to the all other point charges? The answer is simple. Total force on Q1 is the vector sum of all the individual forces on Q1 due to the other point charges. Remember that the force between any 2-point charges is unaffected due to the presence of other charges. For example, force between Q1 and Q2 is unaffected due to the presence of other charges, or force between Q1 and Q3 is unaffected due to the presence of other charges. Now suppose force on Q1 due to Q2 is F12 vector. Force on Q1 due to Q3 is F13 vector. Similarly, force on Q1 due to Qn is F1n vector. So, total force on Q1 is F1 vector equals to F12 vector plus F13 vector plus so on till F1n vector, or F1 vector equals to summation I equals to 2 to n F1I vector, or F1 vector equals to summation I equals to 2 to n 1 by 4 pi epsilon 0 Q1 Qi by square of mod R1I vector into R1I cap. Similarly, we can find the total force on Q2 due to the other charges. Okay. Now, we are going to discuss what will be the electrostatic force between the 2-point charges situated in any medium other than vacuum. Suppose 2-point charges Q1 and Q2 separated by a distance r and situated in any medium. Now, what we obtained from Coulomb's law? Electrostatic force F equals to electrostatic constant K Q1 Q2 by R square. And what we discussed about electrostatic constant, that the value of electrostatic constant depends on the nature of the medium between the 2-point charges and also the system of units chosen to measure force, distance and charge. So, it is clear that the value of electrostatic constant depends on the nature of the medium between the 2-point charges. K is different for different medium. Now, in SI units, electrostatic constant K written as K equals to 1 by 4 pi epsilon. So, electrostatic force F written as F equals to 1 by 4 pi epsilon Q1 Q2 by R square, where epsilon is referred to as absolute permittivity of the medium. We know absolute permittivity of free space epsilon 0 is equals to 8.854 into 10 to the power minus 12 Coulomb square per Newton per meter square. Remember that absolute permittivity of any medium always greater than absolute permittivity of free space. So, from this equation, we can say if Q1, Q2 and R if remains fixed, then higher the value of epsilon, lower will be the value of force. Now, we consider Q1, Q2 and R remains fixed, and we consider three situations. Here, the 2-point charges situated in vacuum. Here, the 2-point charges situated in medium X, and here the 2-point charges situated in medium Y. Now, if the electrostatic force between the 2-point charges in this situation is F, then in SI units, F equals to 1 by 4 pi epsilon 0 Q1 Q2 by R square. Now, if we consider that the absolute permittivity of medium X is epsilon X, which is equals to 2 epsilon 0, then what will be the electrostatic force between the 2-point charges when situated in medium X? Suppose the electrostatic force here is Fx. So Fx equals to 1 by 4 pi epsilon x Q1 Q2 by R square equals to 1 by 4 pi 2 epsilon 0 Q1 Q2 by R square equals to A by 2. Now, if we consider the absolute permittivity of medium Y is epsilon Y, which is equals to 10 epsilon 0, then what will be the electrostatic force between the 2-point charges when situated in medium Y? Suppose this force is Fy. So, Fy equals to 1 by 4 pi epsilon y into Q1 Q2 by R square equals to 1 by 4 pi 10 epsilon 0 Q1 Q2 by R square equals to A by 10. Now, from these three situations, we can say when the distance between the two particular point charges remains fixed, then the electrostatic force between the 2 point charges is maximum when they situated in vacuum, and if they situated in any medium, then the medium opposes the electrostatic force between them and reduces its value compared with the vacuum value. So, we can say a medium with high absolute permittivity reduces appreciably the electrostatic force between the 2-point charges compared with the vacuum value. Okay. Now we introduce a term, relative permittivity of the medium, which is denoted by epsilon r. The relative permittivity of a medium is defined as the ratio of absolute permittivity of that medium to the absolute permittivity of free space. Epsilon r is also denoted by K. K is called the dielectric constant of that medium. Now we can write epsilon equals to K epsilon 0 or epsilon equals to epsilon r epsilon 0. So equation 2 can be written as F equals to 1 by 4 pi epsilon 0 Q1 Q2 by Kr square, or F equals to 1 by 4 pi epsilon 0 Q1 Q2 by epsilon r square. Now remember that dielectric constant of vacuum or free space is K equals to 1, and dielectric constant of air at 20 degrees centigrade is equals to 1.000528, and in many cases we consider the dielectric constant of air to be 1. One thing to be remembered that the dielectric constant of a medium usually decreases with increase in temperature. For example, dielectric constant of water at 20 degree centigrade equals to 80, and at 25 degrees centigrade dielectric constant of water is 78.5. Now we consider two situations. Suppose 2-point charges Q1 and Q2 separated by a distance r. Now Q1, Q2 and R remains fixed or same 2-point charge, same separating distance between them. Here the point charges situated in vacuum, and here the point charges situated in any medium. If in this case the electrostatic force between the point charges is a vacuum, then in SI units we can write a vacuum equals to 1 by 4 pi epsilon 0 Q1 Q2 by R square. In this case, here the point charges situated in any medium. Now, if we consider the electrostatic force between the point charges is F medium, then in SI units, F medium equals to 1 by 4 pi epsilon Q1 Q2 by R square. Now, if we divide equation 1 by equation 2, then a vacuum by F medium equals to 1 by 4 pi epsilon 0 Q1 Q2 by R square by 1 by 4 pi epsilon Q1 Q2 by R square equals to epsilon by epsilon 0 equals to K, or dielectric constant of that medium. So, from this equation we can say that dielectric constant of a medium may be defined as the ratio of the electrostatic force between the 2 point charges placed at a certain distance apart in vacuum to the electrostatic force between the same 2 point charges placed the same distance apart in that medium. Okay. Now, we obtain from Coulomb's law that the electrostatic force F between the 2 point charges Q1 and Q2 separated by a distance R equals to K Q1 Q2 by R square, where K is electrostatic constant. Now, if we consider that the 2 point charges situated in any medium other than vacuum, then in CGS system electrostatic constant K written as K equals to 1 by capital K, where capital K is called the dielectric constant of that medium. Now, the electrostatic force F can be written as F equals to Q1 Q2 by capital K R square. So, this is the mathematical form of Coulomb's law in CGS system for any medium. Okay. Now, problem number 5. The force of attraction between two charges in vacuum is 40 Newton. When the charges are kept in a medium at equal separation, the force of attraction reduces to 5 Newton. Calculate dielectric constant of the medium. Suppose dielectric constant of the medium is capital K. We consider the charges are Q1 and Q2 and separation between the charges is R. When the charges are situated in vacuum, then electrostatic force of attraction written as F vacuum equals to 1 by 4 pi epsilon 0 Q1 Q2 by R square. And when the charges are situated in given medium, then electrostatic force of attraction between them written as F medium equals to 1 by 4 pi epsilon 0 Q1 Q2 by KR square. Dividing equation 1 by 2, we get F vacuum by F medium equals to K, or K equals to F vacuum by F medium, or K equals to, here F vacuum is 40 Newton and F medium is 5 Newton. So K equals to 8. So the dielectric constant of the given medium is 8. And I am ending today's discussion here.